So without graphing, determine if each is an exponential growth function or exponential decay function. So it's pretty easy to tell if something is a growth or decay function because all we're looking at is the factor or the growth or decay factor, depending on which it is, that's attached to the base, or that is the base for your exponent. So in this problem, we're looking at whatever number is attached to the exponent. We're looking for the base. So if we look at these values, if it's larger than 1, it's growth. If it's smaller than 1, it's decay. So for the first one, 2 to the power of x is growth. That's it, because it's larger than 1. 4 is larger than 1. 2 would be growth. 1/4 is smaller than 1, decay. 1/2, smaller than 1, decay. 5/2, a fraction, but still larger than 1. 5/2 is larger than 1, so this would be growth. And 1/2 is decay. So figuring out if it's going to be a growth or decay function is either you're looking at the multiplier, the base for your exponent there. That tells you what it's going to be. So that at least gives you an idea of when you go to graph it, what you should kind of be looking for. So if we look at number 7, I know that this is going to be a growth function. So my graph, when I put it on my plane over here, my coordinate plane, it should be going away from my asymptote. So if we do this, y-intercept, horizontal asymptote, domain and range, I'm going to do the horizontal asymptote first. That's the number at the end. So in this case, there actually is no value. So the horizontal asymptote will be at y equals 0. Domain is always negative to positive infinity. I'm going to draw in my asymptote down here. And I know that this one's going to be above, so the range is going to go from that asymptote to positive infinity. Remember, it just approaches that asymptote, so we're never actually reaching or touching it really. We're never going to get to that value of 0. We're just going to get super, super close, like closer and closer and closer to it. So for these, domain and range, you're always going to have parentheses. No brackets are ever going to be included in these. So the y-intercept is when x is 0. So we can actually plug that point in for our table a while if we want. So if we solve for, and I'm going to do this by hand, this will be on the non-calculator section for you guys, 1/3 times 3 to the power of x. Times 3. What are we plugging in for x? 0. And there's no value being added to the end of it. So, this is where your exponent rules come into play, and you guys have to remember them. 3 to the 0 power, anything to the 0 power is 1. So 1 times 1/3 is going to be 1/3. So we plugged in 0 there. Now let's plug in -1. So 3 to the negative first power, we can't have negative exponents. So our exponent rules say that we move that 3 to the bottom and it will actually become 1/3. So 1/3 times 1/3 is 1/9. So we plugged in -1 that time. Now we're going to plug in 1, 2, and 3 yet. So y equals 1/3 times 3 to the first. 3 to the first is 3 times 1/3 is 1. Y equals 1/3 times 3 squared. 3 squared is 9. 9 times 1/3 is 3. Multiplying by 1/3 is the same thing as dividing by 3. So 9 divided by 3 would also be 3. So we plugged into that time. And let's just plug in 3 yet. So y equals 1/3 times 3 cubed. 3 cubed is 27. So 27 times 1/3, or 27 divided by 3, equals 9. So we can go ahead and plot those points. I'm going to write my y-intercept up here as 1/3. So for these, the domain is always going to be negative to positive infinity every single time for your exponential, whether it's growth or decay, always domain negative to positive infinity. So -1 1/9, 0 1/3, 1 1, 2 3, 3 9. And we'll just kind of squeeze it up here. And then just kind of draw it in. So remember, when we are graphing these, we're just coming down and getting closer to that asymptote. Like we're just going to get numbers that are smaller and smaller and smaller. They're going to get closer and closer to 0. So you kind of want to just draw that graph coming down and sort of leveling off there. There aren't ever going to be any values past that horizontal asymptote.